Welcome back to ajspeller.com. In today's tutorial, we're going to model this related rates problem. A ladder 25 feet long is leaning against the wall of a house. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. Consider the triangle formed by the wall of the house, the ladder, and the ground. Find the rate at which the area of the triangle is changing when the base is 7 feet, 15 feet, and 24 feet from the wall. And here is all the work that we've done analytically in a previous tutorial. All right, what I've done is I've placed all those numbers into a chart here so it's more easily seen, and we're just going to recap a little bit of that information using this right triangle. So remember that we call the ground here X, we call the wall Y, and we're going to call the ladder L. We can relate the Pythagorean theorem to this particular problem, this particular diagram. So here we have x squared plus y squared is equal to L squared. At this point, I want to make this equation here into a parametric equation so that we can model the changes over time. So here we're going to set x equal to the variable t, and remember that the coefficient is understood to be a 1, and that says for each time unit we want the x value to change 1 unit, but for this problem we want the x value to change by 2 units for each time unit. So what we do is let's change this that 1 here into a 2, and now we're going to rewrite the Pythagorean theorem with a 2t in place of x. So here we end up with the quantity 2t squared plus y squared is equal to L squared. And our goal here now is to solve for y. So we're going to end up with y squared is equal to L squared minus the quantity 2t squared. We subtracted this quantity from both sides, and to get y, we need to take the square root of both sides. So in doing so, we see that y is equal to the square root of L squared minus the quantity 2t squared. All right, now before I continue, let's talk about how we make these equations dynamic so that when we move these sliders, our diagram here or our model moves accordingly. So we don't want to use constant values if we can help it. This 2 here corresponds to the value for dx dt, but what we have is a slider so that we can dynamically change that. So this 2 can be replaced with the variable dx dt. And we also have a slider for the variable t for time, and that slider has a name of time. So what we see here is that the distance x can be calculated by taking dx dt and multiplying that by time. And if we use that, if we use this expression for x, we can substitute that back into this equation for y. So here we have y is equal to L squared minus, again, instead of the 2, we're going to use dx dt. And instead of the t, we're going to use time. And then that quantity is squared. Now, this y here is the same as this y, so I'm not going to rewrite that entire expression here. But I know this here signifies, or this equation here signifies the distance from the top of the ladder to the ground. Now, with that information, I'm going to begin working on the equations that I need for the area of a triangle. Well, we know that the area is equal to 1/2 the base. Well, the base is x and the height is y. So area is equal to 1/2 x times y. I'm going to do a similar substitution. I'm going to say I want the x value to equal t. And because the rate at which we're changing in this example, we're just going to say is 2. But I want to make this more dynamic, so I'm really going to make this dx dt times time, which is the same thing we used when we got up here. Now I'm going to rewrite the equation using this expression. So here I have the area is equal to, you know what, let me change the color. The area is equal to 1/2 times x, which is the dx dt times time. And I want to multiply that by y. Well, y is seen by with this expression here, which is the square root of L squared minus dx dt times the time, and that quantity is squared. So now we have a parametric equation for the area. So in the first expression, we're going to enter this expression here, and for the second expression, we're going to enter everything that you see here. So let's go ahead and do that in the model. So we come to the model and let's input the keyword or the function curve. We want the curve that has two expressions. The first expression, as we said, is going to be dx dt times time. The second expression is going to be a little bit longer. That's where we have the 1/2. Oops, let's do that right. The 1/2 times dx dt times time. All that multiplied by the square root of the ladder squared minus dx dt times time. And remember, dx dt times time, that symbolizes the distance of the bottom of the ladder from the wall, and then that quantity is squared. And again, I think it's pretty self-explanatory, but the ladder here is the length of the ladder, and that's being squared. And again, that's all seen here with these various sliders. Our parameter variable is going to be time. Our start value is going to be 0, and our end value is going to be ladder divided by dx dt, and that just dynamically figures out how much time it takes for this model to complete. Then I press enter. What I want you to notice here is that the x value here, it symbolizes the distance of the bottom of the ladder from the wall, and the y value here is the expression is for the area of the triangle. And let's go ahead and turn. We see it created a curve. We don't need to see that curve. Let's go ahead and turn that curve off. And what I want to do now is let's go ahead and show what the current area is of the triangle. Well, to do that, we're going to take text, and we want a text object, and that object that we want the y value. So I type in y. I want the y value for the curve A, and actually I'm going to rename that curve in just a minute. A at a moment in time. So I type in time, so it grabs whatever value that the timer is currently set at. And then here we see it actually calculated what that area is. Matter of fact, let's go back here and let's change this from A to triangle area. All right, and then that updated what we just typed in here automatically. All right, so we see that what it did was it took 20 times 15 and took half of it. Well, half of 20 is 10, and then 10 times 15 does give me the 150 that we see here. What I want to do now is try to clean this up a little bit. So let's put in centimeters for some units. And then let's double click on it and let's type in centimeters squared, then OK. And then let's pull this up so that we can see it. And again, let's go ahead and work on that label. Let's put in here area is equal to that. Whoops, so let's put that back and then OK. And now let's select it and let's increase the size to medium, and let's set it to absolute positioning on the screen. So now as I move the time, we see that we get the current area of the triangle. The next thing I want to do is I need to figure out the rate at which this area is changing. Well, to do that, I just have to take the first derivative. And so with this tool, I just type in derivative. I want the derivative of a curve, and the name of that curve is triangle area. So we're going to find the derivative of this curve that we just created. And now we have the derivative for the x and derivative for y. Here, x corresponds to the distance at which the bottom of the ladder is moving, and this y variable, this corresponds to the amount at which the area is changing. And we have vertical line here. We don't need that for the model, so let's go ahead and turn that off. And the next thing I want to do is let's create a label so that we can place a label on the screen here. So we're going to use something called fraction text. All right, for the fraction text, I want to get the y value, so I type in y from area prime, and I want that at the current moment in time, which is indicated by the timer. So I press enter there, and we see we have this fraction. So let's pull this over, and now let's go in here and let's edit this some more so we can easily see what's going on. All right, here we have feet as the units, but we're doing area, so it really should be feet squared per second. So let's use frac. We have the double curly braces, the numerator. I want feet squared the denominator, I want seconds. For the label in front, I want another fraction. I want the numerator to be dA. I want the denominator to be dt. I want an equal sign in there. And let's do that. And let's just move this up a little bit. And let's go ahead and verify some of our results. Well, let's take a look at what we have. So let's scroll up actually. So here we see that when the x value is 7, the y should be 24, and dA dt should be 527 over 24. So let's set it so this x value is at 7. So here we see x is currently at 11.6. Let's move the time till we get back to 7. And we see we are at 7. We see the current area is 84 centimeters squared. Whoops, and that shouldn't be centimeters. That should actually be feet, because we're dealing in feet in this question. All right, so that's feet squared. And like we said, it's 527 over 4 feet squared per second is how fast the area is changing. Let's take a look at the next one where x is 15, and we see that we should have 35 fourths. So let's set x over here to 15. All right, here at 15, and we have the 35 fourths, and we have the current area at 150. And then the last one, we should have a negative 27 over 7, and the x value should be at 24. So let's set the x at 24. And we see we do have the negative 27/7 feet squared per second. And lastly, we know that we can come up here and press play on the timer, and we see that we can actually have our model here, animate from time 0, and in this case all the way up to 12.5 seconds as we see the ladder hit the ground. All right, that sums up this tutorial by ajspeller.com, and as always, thank you for watching.